Hi, my name is Orko, and today I'm here to present my work, Neural Wave Equation for Irregularly Sampled Sequence Data. And this work was actually accepted in like ICLR 25. So, even before we go to the problem formulation, I'll just like to mention some of the applications. So, of like sequence to sequence modeling. So, one application is actually disease prediction. So, in our case, we actually evaluate on sepsis prediction. So the idea is simple. So you have a patient and you are monitoring their vitals continuously in time. And then from these observations and the timestamps, you need to predict whether that person will have a disease or not. So sepsis prediction is like one of the very standard benchmarks for continuous time data that we evaluate on. Another application that is actually important, I feel, in real life is activity recognition. So basically, a person is fitted with like accelerometer, gyroscope, heart rate monitor, things like this. And then from these activities, so from these sensor readings, you need to predict what activity he or she is doing. So like walking, sitting, running, something like that. So this actually in real life application is actually fall detection. So we know that many of the times we have elderly at our home, and if they fall down and immediate action is not taken, it might be fatal. So basically, activity recognition is one of the ways to solve this problem. Now, having looked into the applications, we actually take a look into the problem formulation. So the problem formulation is actually sort of like simple. So you have got a vector that is one observation arriving at a time step. So you have got a sequence of these observations, and from this sequence you need to predict another sequence or class level. So like we saw previously in case of like activity recognition or suppose sepsis prediction, this class, I mean, this can be a classification problem, but it can also be a regression problem. So one example is in our paper, we evaluate that there is a robot, Walker 2D, that is trained via PPO. And then by looking at its state values at previous time steps, we need to predict what will be future time steps. So that is an example of a sequence to sequence vector regression problem. And now coming to like some of the like what is used right now is a model called ODRNN. So ODRNN is one of the like the staples for handling continuous data, and and like it actually works like a normal RNN with a caveat. So you have an observation X that comes at time step T0, and this gets passed to an RNN cell that produces the hidden state. Now, before another observation comes at time T1, this gap is modeled actually by a neural OD. So the hidden state, it first comes out from an RNN cell, evolves through a neural OD, and then when the next observation comes, the hidden state and the next observation gets combined into another RNN cell, and we keep on repeating this process. So this gives you like a sort of a like a continuous time series model, but with like jumps. So next I would like to tell you this, that even though ODRNN solves the problem of continuous time, it still cannot solve the problem of continuous depth. So what is the meaning of depth here? So in a normal RNN, we'll often stack like RNN layers on top of each other. So that is basically the depth direction of an RNN. Now we found out that actually this depth is an important hyperparameter when it comes to accuracy. And right now there is no way to like actually model this depth continuously in time. So we took inspiration from the original neural OD paper, which says that instead of having like discrete layers, we can have a continuous layer, and then you can use an adaptive step size solver to like sort of tune the depth automatically. So that was our approach. So in our approach, we try to model the time continuously and the depth continuously as well. So this is actually an empirical way to show that why tuning depth is important. The problem with depth in like ODRNN or RNN type architecture is that it is actually not monotonic in nature. So even if you just keep on increasing the depth, the accuracy doesn't like will continuously increase. So it wiggles around, and we figure out that that is probably because of underfitting and overfitting. So here if you see, so this red line is the data fitted with like a neural wave equation, and it actually gives you like the best like MSE without like much hyperparameter tuning. So if we want to model depth and time continuously, uh, then like what are the approaches to do? So one idea is that okay, you have one ODE that models the hidden state evolution continuously in time. Then you have another ODE that models the evolution continuously in depth. So you get a system of basically two coupled ODs, and this can be this can be used, and actually this has been used by like our lab before, the continuous depth RNN. So after that, it also struck us that okay, if we have got two directions like depth and time, can we actually like take inspiration from physics and try to model this behavior as some sort of like a physics model? So basically, we experimented with heat and wave equation. So if you look into this diagram, I'll draw like to draw an analogy. So the continuous vectors that arises at time, like that are coming in time. So these are like this x, so the space direction, and then when they're evolving through the depth, that is like the time direction. So you can get like interesting like evolution behaviors, and there is a bit of a like an information flow that also comes into the picture that makes these things I suspect better than continuous depth RNN. So I'll just go through this slide quickly. So this is just a way to do neural wave equation. So basically, this is the neural wave equation that we try to solve, and this f in the RHS, this is basically uh, the neural network that is learnable, and yeah. So for implementing this, we go through like we actually do a finite discretization of this method, and then you use the neural OD framework to learn the theta via backpropagation. And then this is like an architectural setup. So what happens is data comes in, we pass it through an MLP layer, and this MLP layer then gives us the initial hidden state. So the initial condition is required to solve any OD forward, and then this get passed into a like a PD solver cell where this is like a diamond stencil that we use for solving the wave equation forward, and F is actually the neural network, and then we can use this inside the neural OD framework to learn the thetas by backpropagation, like adjoint backpropagation or backpropagation. And then you can also experiment with different boundary conditions like Newman-Dirichlet and periodic boundary conditions, etc. This is actually, I'll skip this slide for the time. So this is actually the more important slide. So suppose HTD, so this is the hidden state at time t and depth t that you are trying to evaluate. And the interesting thing about using physics is that you can actually get a lot of information from all the layers that is below D. So basically, in case of wave equation, this information flow is like unhindered. But in case of heat equation, what happens is that this information flow is like weighted exponentially. So that is why you can sort of see that the information is diffusing out. But in case of wave equation, there is no diffusion, and like you can think of it like a skip connection directly to each of the layers below D. And then finally to the experiments. So we actually evaluate our model on person's activity, Walker 2D, and sepsis prediction. So person's activity and sepsis prediction are basically classification problem. And then Walker 2D is a regression problem. And as you can see, that neural wave equation actually performs very well in a regression setting. And it also performs like at least beats the baselines in person activity and sepsis prediction. And then this is the complexity evaluation. So basically what happens is when we have a like a time series data, so each data point becomes a matrix because you have got a list of time, and then you have a vector, like you have an entire vector that is the data point. So each data point is a matrix, and then when you have a batch, so it becomes a 3D matrix. But nowadays the ODRNN, like the neural OD framework, they cannot handle this. So most of the previous implementation uses a loop that is very inefficient in Python. So in our case, we actually formulate the problem in such a way that it can be used efficiently. Like the calculation can be done efficiently using matrix, so you can use GPU more efficiently. But that also has a very much huge spike in memory. So in that case, so that is why we use something called gradient checkpointing that drives a balance between the memory and the speed. And then finally, for future work, so of course, like we can experiment with more partial differential equations, and an improved solver framework for PD modeling is actually necessary because the implementation of neural OD type frameworks is very difficult. But I think after flow matching came into the picture, like neural OD systems have become much more scalable. And then of course, because we are working with healthcare, like health tracking and things like that, it will be also be wise to incorporate uncertainty quantification because like PD sequencing might be sensitive to noise. Yeah, thank you.
I'm Okan. I'm a postdoc at Sugiyama Sensei's team, and then the title of this talk is Domain Adaptation and Entanglement: An Optimal Transport Perspective. So this was published in AI Stats last year. And so I want to quickly introduce domain adaptation. So in domain adaptation, we'd like to transfer knowledge that's learned from one domain to another domain. And typically this is formulated in the context of supervised learning. So, or we can call it empirical risk minimization, where we have a risk, it is epsilon of P of F, and then you are trying to learn the parameters of this network F, given inputs X and together with their labels drawn from a static distribution P, right? So in supervised learning, the performance guarantees are restricted to the same distribution, P of S. So in domain adaptation, we relax this assumption. We can consider violations of this IID assumption. So PS, you can say it shifts to a different target distribution from which you don't have labels, right? So what can you do? We typically assume that we have unlabeled samples available from this target distribution. And then the goal is to find a way to update your parameters, this theta of this neural network F, typically, um, such that the network adapts to that environment using those unlabeled samples, such that it still can, for instance, maintain good accuracy in that new environment. So this is what domain adaptation studies. And typically there are lots of different methods that were introduced since the last 10 or 15 years or so. And these are more or less grouped in this domain matching category, where the methods try to match the marginal feature distributions of this source and the target distributions in some feature layer of a neural network. And the idea is intuitively that we shouldn't be able to tell which features belong to which data set during that inference. So we lose that information about that particular data set as the inputs propagate through the layers. At some layer, you shouldn't be able to tell between the source and the target distributions. This is the idea. And typically, people construct different ways of doing adaptation based on this ideal. And in mild cases, such procedures do work well. So you can actually think of this as adapting the decision boundary of a classifier such that it maintains good accuracy under this target distribution, right? But the problem is that typically you're matching marginals, right? So actually there are complications. So you can think of matching marginals as being colorblind. So suddenly these here I put, let's say, feature embeddings with different colors corresponding to different classes and so on. But when you try to match these, you don't have the labels. So actually you just match typically based on some sort of proximity, right, in that feature layer. So in the worst case, what happens is that you match, let's say in this cartoon example, where you want to classify between cats and dogs, you send cats to dogs and vice versa, right? So our goal is to produce a bound on target risk that highlights this issue clearly. Why do we bound target risk? Because we don't have target labels to evaluate that, right? So we can only bound it by some quantities that only depends on this marginal. So yeah, the basic theory that we develop is in two steps. First of all, we bound this target risk based on the source risk plus some Wasserstein distance that depends on the joint distributions P and Q, right? So in X and Y, and also this loss function based on the features and also the labels. But of course, we don't have this target label, so this quantity cannot be evaluated online when we want to do optimization. So we need to decompose it further, and that's what we do. So we propose like a general lemma that decomposes these Wasserstein distances between joint distributions into Wasserstein distances between the marginals plus some sort of conditional term, which we will label later. So using this decomposition and plugging it into the previous lemma, then we get two different bounds. So the first one is useful for analyzing domain adaptation optimization based on source risk plus some marginal distance, right, between the features, and this additional term, which actually then quantifies some sort of conditional distances, which we'll look at in the next slide. So this is useful for analyzing domain adaptation, where you only have access to this. You can only evaluate the first two terms, and you cannot evaluate the last one. Similarly, you can go in the other direction and then bound it using the distance between the label distributions, Py, Qy. And this is useful for further analysis, as we show in the paper. So we cannot go into depth, but please contact me later if you have any questions. So yeah, as I said, this decomposition is useful for domain adaptation where we only have unlabeled samples, so we can only optimize these first two terms. And the last term, however, we show that is very important, and we dubbed this term as entanglement. And in particular, this label entanglement that quantifies the assignment of wrong labels during optimal transport. So we have an intuitive picture for that. So basically, in optimal transport, as you try to kind of match features that are close to each other, right? Source and target features base. You might be actually matching points that have actually different labels, right? So your network was suboptimal, so it actually embedded that target feature close to that source feature. So you end up trying to bring them together. You entangle actually the conditionals of the source and the target, right? This is what is quantified by that last term, which we cannot evaluate during domain adaptation without target labels. And it actually depends, of course, non-trivially on the neural network parameters used to achieve that feature distribution, plus this coupling that is actually being solved by optimal transport, right? So in experiments, we show that this term is very important and depends on the model, optimizer, and the dataset triplet, and cannot be ignored. And it actually explains the um, performance, actual performance of various domain adaptation algorithms. So one very good method can easily become very bad when model or dataset changes. And we observe throughout that in cases where they don't work so well, it is because the conditionals are becoming entangled. So yeah, that was very, very brief, but I hope you could get a little bit of understanding. And if you are interested, please mail me at okan.koc@RIKEN AIP if you have any questions. Yeah, thanks so much.
Hello everyone, I am Sairam, finally a PhD student working with Professor Vineet from IIT Hyderabad. In this short presentation, I am happy to talk about one of our recent works, which we are going to present at CVPR this year. In this work, we developed a compact graphical user interface agent called iSHIFT. Through this design, we show that a compact, lightweight GUI agent can stay very precise if it knows when to think faster and also when to look closer. So, okay, in the next few minutes, I'll explain why this is important and how iShift achieves this. This work was in collaboration with Sarthak from IIT Bombay, myself Sairam, Hemant from IIT Hyderabad, and Professor Vineet. Graphical user interfaces, they navigate visual interfaces through to perform user-defined tasks automatically. For example, so given this home screen of our mobile and we ask what is the capital of Colombia, the agent should be able to automatically navigate through multiple screens and get the final answer. So for example, it has to be able to click on the Chrome icon, then click on the text bar here, type what is the capital of Colombia, get the answer, extract it out, and finally tell us that the capital is Bogota. However, GUI actions are not very uniform. Some actions like swipe and navigation, they just need global context, but precise tabs need fine grounding. So one set of existing works often keep very heavy perception always on to improve precise grounding. For example, just swiping the screen up to open the app drawer does not require precise grounding. It just needs global context of this screenshot. However, if we need to tap on this small icon, which might look similar to other icons on the screen, we need very precise grounding. So to make this precise grounding works, one set of existing works, they use very heavy perception modules and they keep this perception module always on, which wastes a lot of compute. And we also observed that this degrades performance whenever precise grounding is not actually required. So one smart way to deal with this problem is for the model to be able to switch between fast and slow modes. By fast mode, I mean just use the global context and give the final action directly. Whereas by slow mode, I mean whenever precise grounding is required, we need to use more perception modules to get the precise grounding, and then finally, I mean, use that precise localization and then give the final action. Uh, so how to switch between these fast and slow modes is the question here. And a few works on in this direction. They depend on very, external controllers, and they generate long textual loops to decide between this fast and slow modes, which is not optimal. To address these problems, we introduced iSHIFT, which teaches a model uh, to think deeper internally without any external controllers or long text generation loops. And it acts fast when the context is enough, and it only slows down when precise grounding is required. For example, in this figure, we can see that whenever precise grounding, like tapping on this Chrome icon or the text bar here, is required, the model goes to slow mode. Whereas for global context, it just uses the fast mode. So I'll explain this in more detail in the next slide. So here is the core pipeline. We achieve this internal adaptive switching between the fast and slow modes by leveraging something called latent tokens. So the model starts with a screenshot and an instruction, uh, and it then uses latent tokens to judge whether the current context is enough or not. So if yes, so this beginning of token, end of token, this pink tokens here, they represent the latent thinking tokens. So the model uses these latent thinking tokens uh, to judge if the current context is enough, given a screenshot and an instruction. And if yes, then it will just stay on the fast path. So without using this external extra perception module, it just uses the current context and finally gives and directly gives the action. Uh, if not, if it thinks that the context is not enough, it emits something called the perception tokens. And these perception tokens are used in this visual perception module, which is basically a dyno module, and that uses cross attention from the perception module tokens, and it injects localized detail before giving the final grounded action. So we teach this behavior with a strategic lightweight supervision. All the training samples uh, get latent tokens, and only actions that need precise coordinates get the extra perception tokens. So the model learns when to activate the slow path. And our training has three phases. We first align the cross attention projector to learn visual features. We then pre-train the latent thoughts on a large dataset called Android in the Zoo, which has thought pre-training ground truths. And we observed that by pre-training on this large dataset, the resulting implicit reasoning generalizes with meaningful thought patterns well beyond just the pre-training domain. And finally, we fine tune on the downstream GUI benchmarks. We use Qwen2VL as our base model. However, our method can also be easily integrated to our other models. So we report additional results on newer models like Qwen 2.5 VL2. We use 4 diverse GUI benchmarks to show the efficacy of our method. And as this figure and these numbers show, our method, iSHIFT, being a compact 2.5 billion model, it matches or even beats existing state-of-the-art methods with significantly higher model sizes. So for example, if we can see these cyclic cog agent, these use like 20 billion parameters, whereas ours uses like 2.5 billion, and our method is able to reach them or beat them. Yeah, here are a few takeaways. We show that in this work, latent thinking tokens and on-demand visual perception module, they allow adaptive resource allocation whenever visual grounding is required. And we eliminate the use of external controllers or using long text generation loops to maintain high precision across diverse inference layouts. And yeah, as I just showed, experiments demonstrate that our method matches or surpasses very large modules. And yeah, one key point, if I have to say, is that implicit adaptive reasoning in our work is presented as a powerful approach for developing capable and resource-aware multimodal agents. If you are interested in our work, please feel free to check our project website and code. And if you're traveling to the CVPR, we're looking forward to meet you and discuss more. Thank you.
My name is Chao Li. I'm a research scientist working at the tensor learning team at RIKEN AIP. So in my spotlight, I want to talk about the probabilistic modeling via the tensor networks. So in my work, we consider a tensor as a multidimensional array of numbers. It can be seen as a generalizations of scalars, vectors, and matrices. And in our work, we also use the graphs to define, visualize the tensors and its operations. Here in the graph, we use the nodes to indicate the tensor, use the edge connecting the nodes to indicate the direction. So you can see, following this way, we can define and visualize a tensor of any high dimensions. What we need to do is just to add or delete the edges from the node. And once we have two nodes, and if we connect them together, it indicates an operation on tensors, which is called the contraction. What's the contraction mean? The contraction just means a tensor multiplication. You can understand it as a natural extension of the matrix multiplication in linear algebra, but in this case, it's just on tensors. And following this idea, we can construct a quite more complicated graphs, which used to model the complicated interactions among the tensors. And so you can see these two graphs are just two simple examples of the so-called tensor network. So from the examples, you can see what the tensor network mean. They are just a reference to a kind of graph which is used to model complicated interactions among the nodes. In other words, they are used to model the contractions among the tensors. And when we need to use the tensor networks, because the power of tensor network is they can represent extremely high-dimensional problems. The tensor networks can decompose this kind of high-dimensional problems into the much lower sub-problems. Well, all right. So, for the problem of the probabilistic modeling, here, first of all, we suppose we have some ground truth but unknown distribution Px. And after that, we can draw a bunch of samples to have our data set D. And after that, we construct a family of the module distributions QCX, where the theta denotes the learner parameters. So the goal of this problem is just to find the optimal QCX to approximate the Px guided by the dataset D. So from the big picture, you can see this problem should be under the umbrella of the classic density estimation problem. But unlike most of the density estimation method, which is mainly designed for the continuous random variables, tensors are better at discrete probabilistic modeling. Because for the discrete random variables, its distribution can be fully described by a tensor T, which means to identify the mass function Px, which just equivalent to optimize the tensor T. But on the other hand, the challenge is also obvious, that is the dimension exponent, which means that the dimension of the tensor T would grow exponentially in increasing the dimension of the random variable x. So because we have known the power of the tensor network is to solve the cross of dimensionality. So to solve this problem, we can use the tensor network in solving this problem. So in this slide, I summarize three different ideas of using tensor networks to solve this problem. Because of the time limit, I will not introduce too much details. But the basic idea is we use the tensor networks to represent the original high-dimensional tensor T. So the optimization on the tensor T will be replaced by optimizing the values of these much lower dimensional tensors from G1 to Gn. All right, so with this tool, in my work, we applied this kind of methodology to AI for science. Here we are interested in a challenging and important problem in the field of computational neuroscience, which is called the digital brain. Basically speaking, the main idea of the digital brain is to construct computational models for our neural activities. So if we can successfully to construct the data branch like the QCTX, we can do a lot of downstream inference problems. And the neuroscience scientists believe that with the result from these downstream tasks, they can be used to understand the fundamental mechanisms of the brain. All right, so in my work, we constructed the data brain QCTX just with the Tensor network. Here, you can see we choose a very specific Tensor network. We choose this kind of topology because of some physical intuition. Okay, so and as for the learning process, the learning process for tensor networks almost the same to most of the density estimation problem. What we need to do is just to minimize the KL diversity, and in this case, it is equivalent to minimize the negative log likelihood. In the loss function, the values of the joint distribution can be calculated exactly and efficiently by tensor contraction. I will skip the technical details here. All right, so the interesting point is here. So suppose we have learned optimal QCTX, which is described by a tensor network, then we can easily find the quantum circuits, which means that we can construct quantum circuits in which the local operators, the values of these local operators are exactly same to the values of these tensors, which means what we need to do is just need to take these the values of these tensors to encode them into the local operators in the circuits. And once we further compare these local operators with the set of the universal gates, we can deploy the inference straightforwardly on the quantum hardwares. In the slides, we show three figures. They are the estimated distributions of the neural activities estimated from the dataset, classical computers, and quantum computers. So you can see that on the quantum computers, we can get the accurate and consistent results compared with the classic computer. So the last question I want to discuss about that, maybe if you see this result, you would ask, because we can have the same result from the classic computer, so why we need to use a quantum computer? The key point is the computational efficiency. For example, if we want to draw the samples from the quantum computer, for example, like the 10,000s of samples for hundreds of neurons, we can do, if we do the sampling on the quantum computer, it only costs maybe 1 second to 5 seconds. But on the classic computer, we have to cost hundreds of minutes to several hours on the same task. Oh, all right, so this is all I want to share in my spotlight. Thanks for your time.
Hello everyone, my name is Rameshwar, and thank you. First of all, I would like to thank organizers for the opportunity. So I'll be talking about our work, which is efficient and accurate tensor decomposition via recursive switching, which is mainly led by my students Amit and Azhar. So needless to say, most of the real world data sets are often multimodal, and tensors gives a natural way to represent such data sets. So for example, videos which have mode as height, width, channel, and time can be represented using tensor of mode 4. Recommendation system which have user, item, and context as modes can be represented using tensor of mode 3. So as we know, like vectors are tensor of mode 1, matrix are tensor of mode 3, and this cube is tensor of mode 3. So the main problem associated while performing computation with tensor dataset is that when we need to compute some pairwise similarity or distance, such as inner product or Euclidean distance, for tensor which have mode P and dimension longitude mode is D, the time complexity becomes order D raised to power P. And this also requires high memory and storage requirements. So basically, the key idea to handle this large dimension, high model tensor is to compress them into low dimensional vector that closely approximates the corresponding pairwise inner product and Euclidean distance of the original tensor. So mathematically, our goal is to design compression algorithms that take this P mode tensor as input, and dimension log each mode is D1 to DP, and compress it into m dimensional real valued vector where m is much smaller than product of all these di's, such that for two tensors say x and y, their corresponding compressed representation is phi x and phi y. So this inner product of phi x and phi y, which are m dimensional vector, they are more or less very close to the inner product of the original tensor. And of course, this enabled efficient computation and significantly lesser memory and storage requirements. So this falls under the regime of dimensional reduction algorithms, which are kind of, there are quite a few popular dimensional reduction algorithms. And the most popular one is the JL transform, which was proposed in 1984 in the context of compressing high dimensional vectors. So this figure illustrates JL transform. So suppose we have n points in d-dimensional space, which are represented as n cross d matrix. And the task is to compress them into these d-dimensional vectors into m-dimensional vectors, where m is much smaller than d. So their algorithm is very simple. They generate another matrix of size d cross m, whose each entries are sampled from Gaussian distribution with mean zero and unit variance. And the algorithm is just matrix multiplication. Input matrix is multiplied with this projection matrix, and that's how we get the sketch matrix. And they give the guarantee that if we choose m as 1 by epsilon square log n, then the pairwise distance of the compressed vector remains within 1 plus minus epsilon to the original pairwise distance with high probability. So this technique can be also applied in case of tensor. So basically we can consider tensor and vectorize it and consider it as a long vector of size d raised to power p. And we can apply JL transform and we get unbiased estimation guarantee and variance is small. But the main problem here is that running time of this approach becomes exponential in P. So the running time of compressing one tensor of size d raised to power p to a vector of size m becomes m into d raised to power p. Another popular dimensional reduction algorithm is count sketch due to Charikar and all. So I'll just quickly review their algorithm. So their algorithm compress d-dimensional input vector to m-dimensional input vector, m-dimensional output vector using two hash functions. So first hash functions basically assign each coordinate from 1 to d to randomly to 1 to m. Right? And the another hash function is a sign function which assigns each coordinate to a sign either plus 1 or minus 1 with probability half. So to compute a coordinate of the compressed vector, what we do, we just see what all coordinates get mapped to it. For example, in this bin, we get 7 and 1. So 7 is multiplied with minus 1 and 1 is multiplied with minus 1 and we add all of them. So the resultant is minus 8. So that's how we compute the compressed vector. And then they showed that the L2 norm of compressed vectors gives unbiased estimation of L2 norm of the original vector. So the same approach can also be applied for tensors while considering the tensor as a long vector of size d raised to power p, and we get unbiased estimation and variance is small. But again, the issue is time complexity, which is NNZ of vec of x. And when tensor is dense, it can be of order d raised to power p for dense tensor. So these are two classical dimensionality reduction algorithms. Then later on, people showed that the faster algorithm is possible when input tensor is given in some structured form, such as input tensor is given in CP decomposition form. So in that regard, two algorithms were proposed named as tensor sketch. So first one is tensor sketch due to Karen Karnik, which is extension of JL transform. Second one is due to Paham and Pag, which is extension of count sketch. And both approaches give same variance guarantee, while the second one, this one is faster than the first one. And also tensorized random projection, which is an extension of random projection and provides slightly improved variance bounds. So I'll just quickly review CP decomposition. So before, like, we need to understand the notion of outer product. So for suppose we have say two vectors, A1, A2, A3, and B1, B2, B3. Their outer products give a matrix of size 3 cross 3 like this. So in CP decomposition, input tensor is suppose this tensor is of rank R. So this input tensor is given as sum of R rank 1 tensor, and each rank 1 tensor is obtained by taking outer product of these vectors. Like so, outer product of this x1, x2, and x3 give us a rank 1 tensor, and we have R such tensor given to us. We add all of them and we get input tensor. So in this case, we assume that our input tensor is given as right-hand side, right, in the form of right-hand side. Then we can apply tensor sketch algorithm that I mentioned in the previous slides. So I'll just discuss this tensor sketch algorithm. So this figure illustrates tensor sketch for tensor of rank 1, which is given as x1 outer product x2 dot 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 outer product xp, where each xi is in di. Right? So what we do, we generate these random matrices wi of size m into di, and whose entries are from Gaussian distribution with mean 0 and unit variance. So we compress all these x1 to xp using these independent matrices w1 to wp to vectors z1 to zp. And all these zi's are m-dimensional vector now. Now finally, the final sketch is computed by taking element-wise product of all these z1 to zp. Right? And that's how we get the final sketch. Right? So this is for rank 1 tensor. When we have CP rank R tensor, we generate R such copies of these sketches. We get R such final sketches, and we add all of them. That give us one final sketch of m-dimensional vector. Now let's see what guarantee do we get. So the good news is that the time complexity becomes linear in P, whereas in case of JL and count sketch, it was exponential in P. The compressed vectors gives unbiased estimation of squared Frobenius norm of input tensor. But the bad news is that the variance become high. It becomes exponential function of P. Now we'll review the tensor sketch, which is due to Paham and Pag. So again, the input, so this figure illustrates tensor sketch for rank 1. So in X is given as x1 outer product x2 and dot 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 xp. So we generate P such count sketch matrices of size m into di. All of them are IIDs. We compress these vectors x1 to xt using these count sketches, convert the resultant vector into polynomial using FFT transform. Then we take product of all these polynomials and then perform FFT inverse that give us our final sketch. And when we have input CP rank R tensor, we generate R such sketches and add all of them up. And that's how we get the final sketch. So again, the good news is that running time become linear in P, but bad news is that variance become exponential. Also gives unbiased estimation of the sketch L2 norm of sketch vector gives unbiased estimation of L2 norm Frobenius norm of the input tensor. And there is one recently proposed algorithm due to Rakshan and Rabasu proposed in AI-STAT 2020. They also give similar type of guarantee. So basically, they assume that the input tensor is given in CP decomposition form. So X is the input tensor, which is given as factor matrices B1 to BP. The size of each matrix is di cross R prime, where R prime is rank of input tensor. So X can be generated by taking outer product of the corresponding column and add R prime such rank 1 tensor. So this is their input tensor, and they generate a random tensor by the factor matrices. And this each entry of the factor matrices is generated from the normal distribution with mean 0 and variance this. And then they take CP, then they take outer product of the corresponding columns, and all those vectors we get the final random tensor, and then they take inner product of these two tensor. So the guarantee that they get, their running time is again linear in P, and the sketch L2 norm of the sketch vectors gives unbiased estimation of the squared Frobenius norm of input tensor, and they get slightly better variance over the tensor sketch. Their variance is 3 raised to power P minus 1 into this factor, whereas the variance of tensor sketch have factor 3 raised to power P. So variance is slightly reduced. So just to summarize, the state-of-the-art algorithm in the context of developing compression algorithm for tensors. So JL and count sketch, they are the classical one. Their variance is small, but their running time is exponential function of P. Energy of Z can be add by as bad as d raised to power p in the worst case. Whereas these three algorithms, their running time is linear in P, but their variance have exponential function of P. So with this motivation, I'll propose our algorithm, which is adaptation of recursive tensor sketch in the context of tensor compression. So this sketching methods that I'm discussing now was proposed by Ahle et al. In SODA 2020 paper in some different contexts. Basically, and our contribution is that we observed that these sketching methods can also be applied in the context of tensor compression and give us both faster and accurate algorithm. So this figure illustrates compression for a tensor of mode 8. So here we are viewing this tensor as vectorize it and viewing it as a long vector of size d raised to power 8. Each x is of size in RD. So this sketch is like, as you can see, it's looking like a tree, binary tree. So at leaf level, we generate 8 independent count sketch matrix and apply on these x, right? So these count sketch matrix of size m into d. So after application of these count sketch matrix on this vector x, so this resultant tx is a real valued vector of size m, right? So all these real, after application of count sketch, all these input vector becomes compressed into vector of size m. Now all these, this S18 is a tensor sketch of degree 2 by Paham and Park. So this T1 is x is a vector, T2x is a vector. They apply tensor sketch of degree 2 over here. And suppose V1 is the resultant vector that we get. Similarly, from here, this S28 is also a tensor sketch of degree 2. We apply T2, T3x and T4x over here. And suppose the resultant vector is V2 over here. And then V1 and V2 also pass to another tensor sketch of degree 2. And suppose the resultant vector is W1. And similarly, from this side, we get another vector W2. And both W1 and W2 are passed to another tensor sketch of degree 2. And here, from here, we get the final sketch, which is of size m. Right? So there are log p levels of the depth of this tree is log p. So this entire process can be seen as a map of size d raised to power p into m, which can be seen as, so this pi p is a map which takes d raised to power p size input and outputs a m dimensional vector, which can be seen as composition of two maps, two linear maps, QP and TP. So QP is basically we obtain from all these leaf level count sketch, right? So which is basically Kronecker product of T1 with T2 and so on. So the size of TP becomes m raised to power p into d raised to power p. And size of QP is m into m raised to power p. So basically, which is consist of S2, S4, and so on. So S2 is basically what we have at this level. So each SL is Kronecker product of S1L, S2L, and so on. And each SLJ is a tensor sketch of degree 2. And you can see that the time complexity of this recursive tensor sketch is linear in P. And I'll just skip the analysis part in the interest of time. And we showed that, so suppose if Z is our input tensor, then the compressed representation of Z is pi p vec of Z. So this pi p is the recursive tensor sketch that we saw earlier. And this phi Z is the output vector of m dimensional real value vector. Then we show that the L2 norm of this compressed vector gives unbiased estimation of squared Frobenius norm of input tensor. And surprisingly, variance is small. It's independent of P. So we performed some experiments also on synthetic and real world data sets. So in the slides, we have results on synthetic data sets. So basically, we generated random tensors of different modes from small to reasonably large size, and dimension along each mode is 3. So for example, number of entries of this tensor is 3 raised to power 8 and so on. And we use distortion ratio as our evaluation metric. So FZ is basically a norm of L2 norm of the compressed vector, and this is Frobenius norm of input tensor, and this is how we compute the distortion ratio. And the smaller is gives the more accuracy, more accurate algorithm, and we repeated it over 100 and output the average. So this basically this kind of illustrate for different value distortion ratio versus sketching dimension for different values of P and R. So as we can see that when P is small, basically when we have small size tensor, we are able to run JLN count sketch on those input tensor. And then we can see that they are the most accurate one. Red one is our algorithm. But as soon as we increase the value of P, basically when the tensor becomes large, we are not able to run JLN count sketch because the running time is exponential function of P. And the remaining baselines, our algorithm is accurate one, the most accurate one. And as soon as we increase P, this gap increases, right? So basically when P increases, the variance of baseline algorithms has exponential function of P. So they are not accurate one, whereas our is independent of P. So it becomes more accurate. Right? And in terms of running time, our proposal is the best among all the baselines. Right? So it's fastest as well as most accurate for high mode tensor. So we also extend our algorithm when input tensor is given in TT decomposition form. So TT decomposition is another decomposition algorithm available for tensor. So in which the input tensor is represented as, suppose this is input tensor of mode P, it is represented as P minus 2 mode 3 tensors and 2 matrices, right? So say I1, I2, IPth index of this tensor is represented as I1 row, I1 column of this matrix, I2th slice of this tensor, which is a matrix, dot, 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 IP minus 1th slice of this tensor, which is a matrix, and then IPth column of this tensor, which is a vector. And that's how we compute like I1 to IPth index of a matrix. So in this form, we assume that the tensor is given as right-hand side. And then we showed that our algorithm also can be extended when input tensor is given in TT decomposition form. And we obtain similar unbiased estimation and the variance guarantee. Just to summarize, we proposed two tensor sketching algorithm when input tensor is given in CP and TT decomposition form. So our method compressed tensor, high dimensional tensor into low dimensional vector 1 while preserving Frobenius norm and pairwise inner product. So variance of the baselines, they increase as exponential function of P, whereas our method, variance of our method is completely independent of P. And simultaneously, we achieve asymptotically faster sketching time. So, but still there are some kind of open questions remains. So in order to get epsilon delta approximation guarantee on the sketch quality, the dependence on delta is 1 over delta. If you apply Chebyshev on the variance expression. So the question is, can we improve the dependence on delta from 1 over delta to say log 1 over delta? And also there are, if you can apply some other improved variants or of recursive tensor sketch to get faster algorithm or maybe which have less dependency on the randomness. So that's all I had. I'll stop here now for questions.
Thanks, Lord Rameshwar, for a nice talk. So we'll take questions from the audience now.
May I ask a question?
Sure.
So I'm not quite familiar with this field, but do you need to somehow assume that you know the right decomposition, right tensor structure in advance?
Yes. So this algorithm assumes that the tensor is given as CP decomposition form. So that requires as part of our input.
Then in
So,
practice, so given some data, what should I do?
okay, so maybe then one heuristic could be one can apply ALS. So suppose we have given some tensor in raw form, we can apply this ALS algorithm and compute these factor matrices, and then apply this algorithm to get faster conversion algorithm. So that could be one kind of work, one approach that can be tried on practice.
So what happens if the assumed tensor structure is not correct?
Tensor, then basically I need to do kind of analyze it, how far it is from the original tensor, and if we apply on this algorithm, how much error propagates to the final result. That requires some calculation, not think of it.
If the like violation of the assumption is like epsilon, then does the error is proportional to epsilon or something like that? If it explodes, so it's a problem, right?
Yes. So that we need to calculate whether the error explodes or not. It remain polynomial or become exponential in the kind of error. So,
Yeah, thank you very much.
thank you.
Yeah, do we have any more questions from the audience?
I had one question, Srijat Vinith here. Thank you. Thank you, Rameshwar, for the nice talk. My question is a general one, not a very specific one, is how much is tensor decomposition used these days for, say, LLM efficiency or GPU parallelization and so on? I'm just trying to extrapolate this to contemporary application.
Unfortunately, I have not explored that direction, so may not be able to give some kind of precise answer to this.
I see. Okay, but I'm assuming this is used, right? I'm
This
assuming
is
that's a valid context.
Yes,
Okay.
and that is valid context. Yes. But how much it is used in context of LLM or GPUs, that I'm not much aware of.
Sure.
Ramesh, maybe just one question.
Sure.
So how do you think this compression quality is related to the downstream task performance? Does having a good compression correctness always lead to getting a reasonably good performance on any downstream task where this can be used, or can there be another decomposition which can lead to a better downstream task performance? Or can this whole compression can be aligned with a downstream task performance?
So maybe the CP decomposition is possibly used in recommendation system for recommendation. So generating accurate recommendation. So basically, your question is whether these sketching methods can be used or CP decomposition methods can be used.
I'm just wondering, can the sketching methods be aligned in a way that it can end up giving a better downstream task performance rather than making them as two independent things?
Okay. So basically, the sketching algorithm that I discussed, so what they do, they compress high dimensional tensor to low dimensional vectors, such that from the low dimensional vector, we can closely estimate the inner product or Euclidean distance between the original tensor. So basically, it is associated with the corresponding similarity measure that we are interested in. And here the similarity measure is Fubner's norm or Euclidean distance for inner product. So if there is some other similarity or distance measure that you are interested in, then basically we need to come up with different sketching algorithms.
Okay. So this similarity measure is independent of the downstream task, right? So if one can, with a similarity measure which can take that into account, maybe.
Yes. Accordingly, one has to design. So basically, based on the downstream application, first we need to identify what are the similarity measures of interest, and then accordingly, the sketching algorithms need to be tailored.
Okay, sure. I think we have a question on the chat box also. Are you able to see the chat window?
One second. Does every tensor have CP or TT? Yes, every tensor has CP, can be represented in CP or TT decomposition, but TT decomposition can be computed in polynomial time. CP decomposition, like there is some hardness result. Ki first, given a tensor, finding optimal CP rank is NP hard problem. But there are heuristic using which we can get close approximation. And
Okay, good. So yeah, thanks, Rameshwar, for a nice talk. And so I think yeah, if there are any more questions, yeah, please feel free to contact Rameshwar and have any questions. Yeah, thank you.
thank you, Suji.
My name is Qibin Zhao. I'm from RIKEN AIP. Today, I'm going to talk about tensor representation for machine learning. And in particular, we will focus on efficiency and reliability. So as we know now, the large foundation models, we need big data sets and also the huge model size and heavy computational resources. So one question is how we can use the data more efficient, or how we can make our model parameters more efficient, or even the computational efficiency. So our team is working on also tensor method, and our goal is to leverage such tensor method to apply to the machine learning problem and address some issues. Let's start from data point of view, because in many applications, maybe the data sometimes is highly structured and incomplete, and also the data set is limited and low quality, and the data is noisy, or even the data is artificially modified by adversary attack, like adversary examples. So one concern is how can we use the data structure information to help us to make machine learning more efficient. Let's start one simple study, like latent factor models. This is just, we have observation data Y, which are vectors, and we assume there's a latent factors eta. And this is standard linear factor models. So using the data Y, we can estimate the model parameters W and the latent features eta. So the standard way is we can compute we can assume the low rank approximation for covariance. So we first compute the covariance matrix of data, and then we can estimate the W and as well as the eta. So now we check if we have the same data set, but we reorganize the data, like we reorganize the data Y to be a high order tensor. We call this is a tensorization. So we tensorize Y to a high order tensors. Then we assume this covariance matrix become high order covariance tensor. Then apply some kind of tensor decomposition technique to address these issues. Finally, using some experiments show that if we assume such kind of tensor structure, if the data has some kind of relationship between elements, we can capture more structure information. So that means data intrinsic structure and model parameter structures actually is helpful to improve data efficiency. And we can estimate the covariance and some latent vectors with high accuracy. Also, when the data, if we don't use the whole data set, we just sample like a few % of data, and we tensorize data, and we assume this can be represented by a tensor network. And finally, we can reconstruct the data using very few point of elements by solving this loss function. Basically, like this is a fitting area to fit the observed entries, and this is some kind of regularizer to assume the data satisfy the tensor network structure. And this term actually, because low rank structure is very important assumption, so in order to learn the rank, automatically we usually use nuclear norm minimization to encourage we using less parameters to represent same data. So, and this problem is tensor completion. We can show that using high order tensors and the tensor network can really improve the performance for tensor completion task. So the tensor network actually is just a simple extension of tensor factorization or tensor decomposition. Usually we call this for 3D tensors. But when tensor is extremely high order, like arbitrary n-order tensors, we can decompose such tensor by many different structures like a tensor train or a tree structure or this PEPIs and even more complicated structures. And in physics field, tensor network is very powerful tools to represent the many body functions. And in applied mathematics, we consider this is just basic mathematical tools to represent data or models or parameters. Okay, but now the standard tensor network or tensor decomposition has many limitations. For example, we need to assume the structure, like which decomposition, as the previous speaker said, CP or TT, we need to specify in advance. And the second is observation model. We usually assume the Gaussian distribution, which means there is some Gaussian noise assumption. And for particular application, you need to specify the likelihood functions. And the prior distribution is some kind of regularizor. If you encourage the low rank approximation, you can impose the sparsity constraints or sparsity priors. But our goal is to further empower tensor network. Like one point is, can we extend the such linear decomposition to nonlinear decomposition? Or can we capture the more diverse distribution like any distribution without any assumption for the likelihood function? Okay, so we want to consider the nonlinear structure with low rank factorization. And also robustness means if we have a set of tensors, can we improve further the robustness of tensor decomposition by using more tensors? And next is about efficient decomposition algorithm. If we have a new tensor, and can we use previously tensor data, the decomposition models, and apply this model to new tensor data to learn the latent factors more efficient? So one general framework is just using the deep learning technique, which is similar to the autoencoder. And the input is some kind of tensor data. We use some deep learning to learn the encoded latent features. And from latent features to the latent core tensors, we also using neural network to make tensor decomposition from linear case to nonlinear extension. And finally, the output is our estimation of this tensor. In order to model the diverse distribution, we also propose a new technique. Like we can model the joint distribution of latent factors and the data by using such energy function. And within this energy function, the phi, we just use a neural network to model that. In this case, we can model more diverse distribution of data. So that means we don't need to specify which likelihood function, like Gaussian distribution or something. The neural network can model this automatically. And we can even extend the decreased index from integer index to the continuous index. So finally, the tensor can be considered also as a function. So we can also use in tensor to analyze some kind of machine learning problem, which here we consider combinatory distribution shift. So here is an example. If in the training data, we have observed some combinated features and the loss function. So here, this tensor is represented loss function. And we have multitask. So we have a third index. So in this loss function, we only observe some features in some domains, but if the test distribution, like the combination of this feature and this feature we never observed, or some kind of distribution shift. So in this case, loss function is a tensor, and then we use a limited observed element or loss function evaluation to estimate the other part. So in order to do that, we also need to extend the tensor from the discrete index to the continuous index. Then the tensor decomposition is becoming functional tensor decomposition. So then we can use this to analyze mathematically some kind of like a distribution shift problem. Okay, second about model parameters efficiency, and I will present just one of the recent work. I think LoRa is well known for fine-tuning tasks, and we have foundation models, and we need to just fine-tune a small data which assume to be low rank, and the number of parameters will be smaller, and we can easily to fine-tune to the new task. But in reality, if we do full fine-tuning, actually the adaptation part data is not necessary always to be low rank. If the data is not low rank, fine-tuning LoRa is, I think, is not the perfect case. So our question is, can we achieve better approximation to fine-tuning with adaptation of less parameters, less number of parameters? Then we change the LoRa slightly. We propose first we using a transformation adaptation to the foundation original pre-trained W0 and plus a fine-tuning part, adaptation part. So in order to reduce the number of parameters, we assume the T can be tensorized to a high order tensor and then using the tensor network representations. And instead of using low rank assumptions, we assume the tensor network assumptions, because as we showed previously, after tensorization, we can capture more information compared to the directly low rank matrix factorization. So one experiment shows that for this diffusion model to generate image with the text prompt, so our generated image are more close to the text, transparent, the variable, but the other like LoRa or some other method, the generated image is worse than ours. But more important is we try to reduce the number of parameters, and this is some comparison with LoRa and our method. Our number of parameters can be further reduced than this, but the performance and even better than LoRa. And we can also using the such technique to analyze the theoretically how to do tensor regression if the data is insufficient. Also, when we use transfer learning, we face the distribution shift. So we analyze the basic problem like tensor regression, but many tasks. This is a basic tensor regression problem. And if we have a new task, how to transfer to new task. Then we also assume the low rank approximation between the all parameters between tasks as a low rank assumption based on the tensors. So theoretically, we can approve some kind of the error bound, and in this case, we can use tensor method also analyze the theoretical result. So finally, we also talk about reliability of deep learning. I think this is one famous problem, adversary attack and defense. And the two basically technique is adversary training and adversary purifications. So the adversary purification is, we don't need to change the vanilla classifier. We just train a new model, purify model. in order to remove perturbations from the adversary examples. This problem is very similar to denoising task, but the difference is we don't need to difference with denoising task. We don't need to output of the output close to clean image, because our goal is to make classification output is correct. So here, that means we just need to remove perturbations and just keep semantic information. And currently, the diffusion model is a state art for this task. The idea is using the first input more Gaussian noise to destroy the image, and then reverse part to remove Gaussian noise as well as perturbations. However, there's a challenge that it's very difficult to choose the time t. If we choose a large time t, and the diffusion model cannot guarantee the output image is exactly same image as the input. Sometimes the semantic information can be changed. Or if we use a small t, and the adversary perturbations cannot removed very clearly. So in order to address these issues, we must give a diffusion models some kind of guidance to make the output semantic information doesn't change as much as possible. So this is we propose some kind of guidance in order to keep the different time point t, how to make the semantic information close to previous time point t. And also we keep the different samples they have the larger distance. So finally, we show that such guidance can further enhance robustness of diffusion models. Because diffusion model usually is pre-trained model, and it's not specified for this task. We also propose how to fine-tune the diffusion model based on our task. So we just use similarly the same adversary training loss function, but we keep the classification model fixed, and we only fine-tune the diffusion models and to further improve the performance. Finally, we also tried using tensor network to address these issues, because there are some advantage. Tensor networks, we don't need to train a huge model using training dataset. We can just do it online by some new input, which we can using tensor network to decompose data and remove perturbations. But traditionally, our method doesn't work, because tensor network or tensor decomposition usually assumes the Gaussian distribution or some other distributions. But in reality, adversary perturbations distribution is unknown, and it's very difficult to capture it. So we try to use the first solution is using such kind of from coarse to fine technique to address these issues, because when the image to downsampling to a very low image, usually adversary perturbations tend to be Gaussian distribution likely. So then we can first start from the low resolution image using tensor network representations, just learn the first two cores, and we gradually increase the image resolution by adding one more course. And in order to avoid adversary perturbations to be absorbed into tensor representation, we design a new loss function. We're using a delta to try to keep some kind of distance between the estimated data y and with original adversary examples. Okay, now we think about these issues. We need to address many challenges. Mostly we consider clean accuracy and adversary accuracy, but now we also think about if there's a new unseen attack, how to do that. And even the unseen data set because the diffusion model highly depend on the training data set. If the new data set coming, such diffusion model doesn't work well for new data set. Of course, we also need to consider training cost and the inference cost. Using tensor method, one big advantage is we don't need to train a model, so we have zero training cost. But the limitation is because for the inference cost will be increased. So next we will consider how to improve the inference cost. And theoretically, we also show that if we assume low-rank approximation or low-rank tensors for adversary training, and it can be shown that theoretically error bound we also changed to be smaller. So that means such kind of regularizer actually can further increase the robustness. For the large language model, the jailbreak issues, and the people need to learn a prompt. And in this case, if the sentence is long and many tokens, and it's very difficult to optimize that. Here, we show that using tensor method, we can also address these issues. We model the probability of all the tokens as a tensor. Then we can sample some data point using the tokens to get loss function. It's similar to tensor completion for loss function. Because tensor decomposition is, we can decompose this loss function using tensor train or something. So we can do this sampling more efficient. Okay, finally, yeah, in this talk, I just very briefly overview some applications using tensor for machine learning issues, and in particular for how to capture data structure and model parameter structures. And yeah, we recently focused on reliability and interpretability. Also, quantum machine learning is our future study task.
Thanks a lot, Qibin. It's a very interesting talk. So we'll take questions from the audience first. Yeah, maybe I can start with a question.
Yeah.
So in your experience, when you're dealing with these diffusion models or LLMs, did you ever found that, okay, when we use these low rank tensor decomposition or LoRa approximations, different layers may need different ranks, or the change that may need in different layers is going to be different? Or any thoughts on that, like, or just a single rank across all the layers would work?
Yeah. I think you are talking about using model compression for diffusion model or large language model. I think, yeah, rank is very difficult to choose. It depends on your model. Sometimes the weight parameters may not have very good low rank structures. So in this case, maybe the model compression performance is not good. But usually, because the model is over parameterizations, if there are some redundancy, and sometimes low rank needs can reduce number of parameters.
Sure. But is there a principal approach to choose the rank without trying out all the different ranks and seeing the performance on test data? Do you have any suggestions?
Yeah, we have many techniques to choose the rank, but we just think about if the pure tensor problem. If we given a tensor, how to estimate the rank, how to estimate the structure for the given data. But we haven't tried to using such technique to apply to diffusion models, because the model is complicated, the objective function is different. But if we consider a simple problem, given a fixed tensor data, how to learn the rank and how to learn the structure, we have some algorithm to do that.
Okay, sure. Got it.
Yeah, thank you for the questions.
Just one question again from my side, Vineet here. how do these methods change against diffusion models and autoregressive models? And I'm especially asking in the context of, because today there's also a trend to combine them. So I'm just trying to understand, like, fundamentally, do the methods change when you go between autoregressive and diffusion models?
I'm sorry, due to maybe my internet is not good. Can you repeat your question?
Oh, okay. I can also type it. My question was, how do the methods change between autoregressive models, that is like LLMs, text generation kind of models, versus diffusion models where you generate images? Like fundamentally, how do the methods change is what I was asking.
I see. Yeah, actually, our study maybe for the like we using tensor to represent parameters. It's not doesn't related very much to the machine learning task like diffusion generative model or regression because we consider the parameters is a tensor and we try to change the structure to capture the structure parameters. It's not close related to the such kind of different task.
But in diffusion, you have to do the same operation again and again, right? So there is a recurrence or iterative nature of the operation, whereas that is not there necessarily in autoregressive, right? In diffusion, you start from noise and you keep doing the same operation again till you get your image. Wouldn't that have an effect on the method?
Okay, yeah, you are right. Yeah, actually, we haven't applied to this to diffusion. I think it's possible to apply this to the diffusion model. If in each layer, the backward of diffusion, each layer there's a new unit, and we can represent the unit parameters as the tensors. I'm not sure if
Got it. No,
it's
got it.
your
I thought
question or
somewhere,
not.
I thought somewhere in your slides you did talk about diffusion, so that was the
Yeah,
context of my
yeah.
question.
But for diffusion part, we propose the guidance.
Ah, I see.
Yeah,
Understood.
we
Got it.
propose a
I got
new
it now.
guidance for diffusion.
Understood. Got it. Okay. Okay.
Yeah.
Thank you. Thank you.
Thank you very much.
So I'm going to talk about statistics and machine learning as used in astrophysics. So I guess one way this talk is different from most other talks is like I won't talk about one paper or one project. It'll be a bird's eye view and some sort of an overview of different tools and methods of machine learning and statistics as used in different areas of astrophysics. Okay. And some disclaimer, I mean, this is a huge subject and is not a comprehensive review. I'll just give a few highlights of what we have been up to. And I should also add, unlike all of you, I'm not formally trained in machine learning. And I won't also talk about LMM. They are also taking off in a big way in astrophysics. And again, these are some of my collaborators, the ones in Majumdar, the students with whom I've done, based on whose work I'm presenting the result. So I guess the motivation for this whole collaboration is this very nice quote by Professor Narlikar to C.R. Rao. I think one of them is a doyen of astrophysics and another is a doyen of statistics. Unfortunately, both passed away just very recently. So what Professor Narlikar said is in some conference, one normally associates statistics with large numbers and astronomy is full of large numbers. I have every reason to believe that increased interaction between statistics and astronomy will be a benefit to both the subjects. Okay. And now a modern twist to this quote is now astronomy is not just full of large numbers, it's also full of big data, big images. So you also need increased interaction between astronomy and people who work with large data and so on and so forth. Okay, so these are some of the statistical tasks in astrophysics. I won't go through all of them in detail. The ones in blue are just some of the things which I will mention in this talk. Okay. So what is the main difference in astrophysical data and data in other domains? Okay, so this is something I realized after some time. The main difference in astrophysics data is that data comes with uncertainties. Okay, so you have some X control variable, output Y, and the uncertainty in output. Okay, that is. So any regression problem, if you're doing, you must take into account the uncertainties in the uh, uh, in the data. Okay, so I'll just show you this data shows. So this is the most important plot in astrophysics. This is like the Hubble plot. So x-axis is the distance, y-axis is the velocity. This shows that the universe is accelerating. So you can see the uncertainties in this case they are in the x direction. So any regression problem, you must take this into account. And again, this is the simplest level. You can make it more complicated by assuming that the uncertainties are incorrect, and you have to account for the uncertainties of the uncertainties, Gaussian uncertainties, Poisson uncertainties, binomial uncertainties. So this is one subtlety which is not there in, I guess, machine learning from based on I think what I've discussed with you people. Okay. Now, most of what we know about physics and astrophysics has been obtained by analysis of data and using parametric regression problems. Okay, so usually I don't think physics is at a stage where someone comes up with a model and says describes the world. No, it has been based. Someone usually constructs a model, but only way you can test the model is by only way you can validate the model is by comparing it with data and making sure that the results agree. Sometimes the model has free parameters and you need to determine the free parameters. Now, the way this has been, so this can be posed as a parametric regression problem. And traditionally, these parametric regression problems have been solved using frequentist methods by minimizing chi-square or maximizing a likelihood, which is usually Gaussian, but sometimes it's Poisson. So let me just show you one such plot. So this is a parametric regression problem in two variables. And these contours show the 68%, 90%, 99% confidence intervals, which encapsulate the parameters. So basically, if sine squared 2 theta is greater than 0, that means neutrinos have mass, and you can see that it is greater than 0 at a large confidence interval. So this plot earned a 2015 Physics Nobel Prize for discovering neutrinos of mass. Show you another plot. This plot, or actually a modern version, this is an updated version of the original plot which got the 2011 Physics Nobel Prize. This showed that the universe is accelerating. So x-axis is the density in matter, y-axis is the density in lambda, and you have these ellipses show 68%, 90%, 99% confidence intervals. So these are obtained by minimizing a chi-square and by constructing delta chi-square contours. Okay, so you might ask why we need confidence interval. Well, if the uncertainties contain if the input data contains uncertainties, any parameter estimation must have uncertainties also. So we need those also. And if you have two free parameters, obviously you need an ellipse which encapsulates the uncertainties. Okay. But gradually, I think Bayesian parameter estimation has been superseded with Bayesian parameter estimation. And not just that, the number of free parameters have also increased. Okay. So this is an example of 16 parameter regression problem in the area of exoplanets. And so these are solved by, I think, by constructing a posterior given a set of priors and a parametric likelihood function, and you have each of these 16 choose two. If you have 16 parameters, you have 16 choose two contours. These show the contours, and these plots along the diagonal show the marginalized posteriors. Okay. So this has become now this has become bread and butter become very routine for the last decade. Okay, so how do you sample these posteriors, and how do you construct these I think corner plots is what they're called, these marginalized credible intervals, using Markov chain Monte Carlo methods. And the workhorse software which is used in astrophysics is something called EMC. and it is essentially just 3 lines of Python code. Okay, and when I gave a similar talk in 2019 workshop, this code had the paper behind this code at around 2,000 citations. As of yesterday, it has about 12,400 citations. Okay, so why it has so many citations? Because it works very well, and it is simple to use, and essentially it has also been used outside of solving Bayesian regression problem for sampling any posteriors. Okay, so one thing which we did with Srijit and one master student is also so MCMC is good and is very widely used, but sometimes it can get very slow. So we tested it with variational inference and showed that it is much faster than MCMC methods. And this decade also a lot of research has been going on normalizing flows, speeding up the likelihood estimation using Gaussian process. Okay. Something else which is widely used in astrophysics is like parametric model comparison. So let me just explain what that is. So this x-axis is energy. These dots are the data points, which is the time lag, and these are the uncertainties. So the question we want to ask is this data consistent with the pink line, which is the prosaic astrophysical model, or 2 other exotic physics models? Okay, so how do we answer that question? So this area, this kind of this subject is called model comparison or model selection. And the way traditionally people, again, this has been initially done using frequentist methods and information theory methods such as AIC and BIC. But now I think the community has switched to Bayesian model comparison, Bayesian selection. And the workhorse technique for this is, I think, the nested sampling algorithm, which was invented by John Skilling around 2005 or 2006. And this has also become very now routine. And one of the most widely used code which does nested sampling is Dynasty, which is close to 2,200 citations. So let me just show you one plot which compares the natural log of the base factor for, I think, 6 different models for a whole bunch of pulsars. This is some work done by one of my PhD students. So this is used for, I think, model comparison, okay, parametric model selection. Okay. So now I think there's still a lot of research in Bayesian inference on likelihood-free inference. Where you don't have a parametric likelihood, simulation-based inference. This is sometimes called model forward modeling, hierarchical Bayesian inference, estimating p-values of Bayesian inference. So this is this completes sort of the first part of my talk, where we talk about parametric, I think, regression analysis and parametric model comparison. Something else in between is, I think, Gaussian mixture model. So I think all of you know what is Gaussian mixture model. You just model a probability distribution by a superposition of different Gaussians. A bunch of astrophysicists from NYU then extended Gaussian mixture model to take into account uncertainties, and this code they named it XDGMM. So we applied XDGMM to gamma ray burst data. We use it to model to do clustering in log hardness versus log T90, which are 2 parameters of gamma ray burst, to find the optimal number of clusters and to select the optimal number of components. We use AIC and BIC. So basically, you can see for BIC, you get a nice minimum for 2 components, whereas AIC, you get a minimum at 3 components. And so this work was again done by Srijit and 2 other UG students. One thing is, I think, just aside, is that the first version of this paper came out in 2017, but it was published after 5 years. I mean, this is sometimes happens. We work with undergrads, and then we had pandemic and other things. Okay, so now I switch to, I think, machine learning. Again, machine learning is also, I think, has become ubiquitous in astrophysics. It's used for a whole bunch of stuff, which I won't go through into the detail. So I'll just give you a few examples, okay, of some of the work we have been doing. One one area is to remove cosmic rays and satellite trails from images. Okay, so if you see these pictures from Hubble Space Telescope, they look very nice and pretty and very pristine. But one thing which is not mentioned, they contain a lot of crud, like from cosmic rays, satellite trails, and those need to be removed, or sometimes I think interpolated away. Okay, and the traditional techniques are very computationally intensive. So one of Sumona's student, I think Srinath, applied, I think, attention augmented deep learning to this problem, and it worked pretty well. Okay, so again, I won't go into detail into this architecture. I'm not an expert, and this shows the performance of these attention augmented deep learning methods to this cosmic ray masking, and it sort of does pretty well. So here you can see that it identified the cosmic rays. Okay, something else which he did is object classification. Now, certainly, so what is object classification? If you look at astronomical images, you have stars which appear like points, you have galaxies which appear extended, and you have quasars which also appear like point, but there are some subtle differences in their photometry. So I think what Srinath did is he applied vision transformer models to the problem of object classification. And again, this is I think the architecture he used. And these are some of the algorithms he used: MarchNet, MMVIT, and so on and so forth. And these are the kind of accuracy, precision, and recall which he got for different combinations. So this is on Sloan data. Something else which I think Raghav did, who was I think a MTech student in the CS department with Srijit and me, he applied, I think, neural ordinary differential equations. I think Srijit talked about it today morning. Unfortunately, I missed that talk due to class. So he applied this problem to galaxy morphology classification. So what is galaxy morphology classification? Galaxies come in all shapes and sizes. So you want to do some sort of a systematic pattern recognition. For that, he used, I think, ResNet, Node, and Node ACA. He compared that, and so this is an ROC curve for that. Something else which I don't think anybody has mentioned in this meeting among the talks I attended is something called symbolic regression. So what is symbolic regression? So symbolic regression, so given an input data and an output data, symbolic regression tries to reconstruct in an ab initio way the parametric function or the mathematical function which describes the relationship between x and y. Okay, and so this is a paper which Rachit Deshpande, who's an MTech student in the AI department, and I have put out. It's still under review, but it's out on arXiv, where we tried 4 different symbolic regression to the problem of object classification. And so these are the different parametric models we came up with, and so these are the confusion matrix, and these are the objective functions which have been used. Okay. Okay, so I think that is it for a bird's eye overview. If you want to learn more about this subject, you can look at astroml.org, which is a bunch of Python tools for doing a lot of the bread and butter tasks and some modern areas also. Okay, and if you have some ideas for improving some of the things which I talked about, I think do let me know. Okay, so I think I'll stop here. Yeah, I'm happy to take questions.
Thanks a lot, Shantanu. So, yeah, we'll take any questions.
Yeah, so may I ask a question?
Yeah,
So thanks for the great talk. It's amazing. So a lot of machine learning techniques are applied to astrophysics, and that's great. So my question is not about research itself, but the research style. So this is something we really want, right? So we are doing machine learning, and we hope our techniques can be employed in like science context. But this is always challenging because like machine learning people cannot understand like astrophysics, for example. So in your case, how did you like made such lot of collaborations successfully? So this is amazing to me.
Yeah, so okay, so that's an interesting question, right? So it is a little bit of a give and take, right? So as I mentioned, I'm not trained in machine learning, so I tell them that this is the problem, and then usually the people, the domain experts in machine learning, they tell, okay, we can use this, okay, and the student who works on this, okay, in most cases it is the students is from an ML background. If they have like questions about the domain knowledge, then they come to me. Okay, so it's a little bit of a give and take. And I should also mention, right, in Tokyo there is a IPMU, okay, Kavli IPMU at Kashiwa. Okay, they have people working on cosmology, and they also do some machine learning. Okay, so I guess you can talk with them to find out. But yeah, it is a challenge, and there is also a little bit of this thing in astrophysics and in physics. I think we are judged by refereed publications. In machine learning, I think you are judged by conference proceedings. Yeah. So there's a little bit of a give and take. Okay, that's how I would put it. I don't know, Srijit, if you want to add anything.
Yeah, that's true. So I have been collaborating with Professor Shantanu since the time I joined IIT Hyderabad on astrophysics related problems, applying the techniques in machine learning, in Bayesian learning, etc., in deep learning to solve problems in this. Yes, I think this is how the collaboration works, that we have this domain expertise from both areas coming together, and then we'll have students working on these problems where we can apply deep learning, machine learning techniques for astrophysics. Yeah, things generally work. Yeah, maybe. Yeah, that's all.
Yeah, so like in my case, the challenge is always the problem formulation. Like there are a lot of like issues, problems in like physics or chemistry or some other science field, but we need to formulate their problems in terms of machine learning, right?
Yeah, so
We need to.
I think you have to essentially discuss with this thing. You have to discuss with some domain experts initially, just to talk what kind of problems they have, what kind of problems they struggle with, and obviously I should also add that some advances, like what are the unique niche cases, like for example in astrophysics I mentioned, right, the data has uncertainties, okay. And most machine learning algorithms don't automatically, as I understand, take into account the uncertainties. Okay. So this is a brand new area of, I think, research which nobody has looked at. Okay. Although if you really think about it, right, any image has uncertainties. Okay. So in some sense, even you people should take into account uncertainties. But anyway, the short answer to the question is, I think you should, the easiest way to get started is just to talk to people who work in astrophysics and who have applied some machine learning and statistics. Okay. And there have been books written, just like, so this astroml.org, right? That has been written by, again, astrophysicists who learn machine learning on their own. Okay. And so you can look at that book and anyway, I can give you the names of some experts at Kavli IPMU, okay, with whom you can talk, in Kashiwa.
Actually, I'm from Tokyo, and I'm also director of RIKEN AIP. And
Okay.
last year, we invited one professor from IPMU as a team
Okay.
director. Maybe Yoshida, Naoki Yoshida.
Oh, yeah. I know, yeah. I know of him very well. I don't personally know me. He's a very famous astrophysicist. Okay, so you've started this conversation, so I think it should be
and
fine.
he's part of RIKEN now. So
Okay. Nice. Okay, so I think you just discuss with them, and occasionally I think some effort also has been spent on your part to just read some of these papers, how machine learning has been used in some of these astrophysics papers, and so on and so forth. Okay, so I'll just make one comment, not about machine learning. Okay, so this Penn State has a very strong astrostatistics group. Okay, and then what they found was that astrophysicists they did not use some of the statistical tools properly or correctly. Okay, so it's possible that when astrophysicists are using machine learning, they're not doing it properly or the way it should be done also. Okay, so there's a lot of scope for I guess innovation of and so on and so forth. Okay, hopefully that answered your question, I think.
Yeah, and that's amazing. So thank you very much.
Is there any other questions? So maybe just a general question: how do you see the use of the latest advances in AI, like large language models?
Yeah, so that is taking off in a completely new way, including writing full papers and from scratch also. Okay, I mean, do this analysis and so I think that's going to revolutionize. I think I mentioned that I purposely not talked about LLMs, but yeah, that is going to that is already revolutionizing this, I think, astrophysics. I mean, where I've used LLM the most, I mean, is to solve compilation problems, some of the software which involves C, involving make files and other things, right? I always struggle with installing it on Linux clusters and all that. Now that has become very seamless using this chat GPT and all that. But again, I'm also not, I've just got my feet wet with LLMs. Okay, so I myself have not exploited the full way, but some people are already way ahead. So maybe in the next workshop, I'll have a better answer.
Sure, got it. Yeah, a follow-up question was like, are there some foundation models in astrophysics which can address some specific problems in astrophysics? Yeah, perhaps, yeah, I think we could be able to discuss it.
Yeah. So again, foundation problems as such is, see, again, most of what we know about astrophysics is from analysis of data itself. Okay, so yeah, so all machine learning tools can be used. Okay, now one thing I think people have now used symbolic regression to rediscover Kepler's laws and some of the laws of physics. Okay, so in some sense, I think maybe symbolic regression is one way to sort of rediscover some of the laws of astrophysics, if that's what you mean by foundational models.
Sure, maybe we can discuss this.
Sure.
One thing I can add is, so you computed the confidence interval, or you perform statistical test, computed p-value. But
Yeah.
nowadays we use data to generate a hypothesis, then use the same data to evaluate the generated hypothesis. Then actually the computation of p-value naively is biased, or confidence interval is biased. We need to actually adjust it. So it's called post-selection inference, and one of the teams at RIKEN AIP is fully working on this topic. And this might be quite important in like science domains, including astrophysics, because now people use machine learning algorithms to generate a hypothesis.
Yeah, so this comes into simulation-based inference, forward modeling. And traditionally, Bayesian inference does not calculate p-values. Okay, it only believes in model comparison. But people have somehow misused or abused Bayesian inference to calculate p-values also. Okay, and people have done that. But traditionally, in Bayesian inference, there is no p-value. So
right.
But yeah, what you mentioned, the first part, that is simulation-based inference or likelihood-free inference. Yeah.
Great. So this can also be a kind of common topic we can discuss in the future.
Yeah, if there are no other questions, yes, we can end up the talk. Like, thanks a lot, Chandana, for this nice talk.